with the given equation, we can write like that: omega equals to 2 pi f, so f equals to omega by 2 pi. Omega is a radian, this is given with the 314, and a 2 pi, pi is again the value of pi is 3.14. So by putting all this value in the equation of f, we can write we can find that f equals to 50 hertz for that given current. Now the angular frequency, that is omega equals to 314 radian per second. This already we all know. The next, that is the IRMS. The equation for IRMS is IRMS equals to Im by root 2. Now we have we have find the value of Im, that is 70.7. So by taking the ratio of 70.7 with the root 2, we can find the IRMS value for the current, that IRMS equals to 50 ampere. So the maximum value of the current is 70.7 and the average value for that particular current is 50 ampere. Now the time period, that is t equals to 1 by f. As we already proved that the frequency for that current that circuit is f equals to 50 hertz. So by taking the ratio of 1 by 50, that is t equals to 1 by 50 equals to 20 millisecond. Now the next average value, that is IAV, that is nothing but the 2 Im upon pi. This is one extra value or extra parameter which we prove for the given circuit. IAV equals to 2. Now the Im is 70.7 and the value of pi, that is 3.14 or 0.707. You can put anything, 3.14 or 0.707. So by taking the ratio of we just find that IAV equals to 45.03 ampere. Now the next question, the question for A, state the advantage of three-phase system over the single-phase system. Why the three-phase system or why the polyphase system is much advantageous or much preferable than the single phase system? The 5 marks question. So you have to just give the 5 to 6 reasons why three phase is much preferred than the single phase system. Starting with the size. For the three phase system, the size of the circuit is very small than the single phase circuit with the same rating. That's why it is much preferred for where the size is matter, then the three phase system is preferred than the single phase system. Then the cost, again for the same rating, the cost of three phase system is very less than the single phase system. So first one is a small size, second reason is low cost. The third one, the better power factor. For the same rating, the three phase system gives the much power factor than the single phase system. It means that there is a very less heat is lost in a three phase system than in a single phase system. This is very important reason why three phase is again much preferred. The fourth one is rotating magnetic field. Due to that rotating magnetic field which is produced in a three phase system, it can be a self started. Friends, remember one thing, single phase system is not self started because there is no rotating magnetic field is generated in a single phase system, but that thing is solved in a three phase system, because in a three phase system or in a polyphase system the rotating magnetic field is generated. That's why the motor is self induced. There is no alternate or there is no other source of EMF, induced EMF is required to start the motor in a three phase system. So it is again very important advantage. It required very less copper. For the same size in a single phase or in a three phase system, it requires very less copper. Friends, as we all know that copper is a very costly material, that's why so there is a always necessary in a copper for getting a good conductivity in a circuit. So it requires the very less copper in a three phase system due to in a single phase system. The flexibility, again it is a very important parameter. Flexible, the system is very flexible three-phase system is very flexible than a single-phase system. You can easily obtain the single phase among the three-phase system, but you can't convert the single-phase system into three-phase system. But you can easily convert the three-phase system into single-phase system. So there is a flexibility provided in a polyphase circuit or in a three-phase circuit. It gives the steady output. The three-phase system gives very steady output than the single-phase system. It means that the output in a single-phase system is a very fluctuating. It is not a constant, or it will not steady. But that problem is not happen in a three-phase circuit. The output in a three-phase circuit is a very steady or simple, or you can say that it's a constant. Smooth DC output. If the number of phases are increased, then DC becomes very smooth. It means that in a single phase system the DC is not as smooth as DC is smooth in a polyphase system. Explain the effect of the next question, that is the temperature, effect of temperature on conducting material, insulating material and the semiconductor material. This is our last question in our paper. As we all know that the conducting material, the material which have the best or the higher conductivity than another material, insulator or semiconductor. You can say that in another word, the material which having the less resistivity or less resistance is known as the conductor or conducting material. Friends, the material which having the higher easily pass the current through it is known as the conducting material. So as the current passing through the material, the temperature goes high. So we can say that in a conducting material the effect of temperature is very high. So whatever if you are gradually increasing the value of current, the temperature suddenly goes high in a conducting material. Now in a semiconductor material, the semiconductor material are those kind of material which resistivity and conductivity are in between the conducting material and the insulating material. It means that the material whose conductivity is not higher than the conductor, but it is lesser than conductor and it is higher than insulator. You can also, in another words, we can say that the material whose resistivity is higher than conductor but lesser than insulator are all these kind of materials are known as the semiconductor materials. Semiconductor materials are, many times we can observe that the semiconductor materials are experience the negative temperature of coefficient. It means that if you are increasing the temperature, this kind of materials experience the negative resistance. Generally what happens, if you are increasing the temperature, your resistance are increasing. It is there, this kind of material is known as the PTC, positive temperature of coefficient, and whatever the materials are the negative temperature of coefficient, it means that if you are increasing the resistance experience are the negative if you are increasing the temperature. Now the third one is the insulating material. Insulating materials are those materials whose conductivity is very less but whose resistivity is very higher. So the material whose resistivity is higher than semiconductor and conducting material but whose conductivity is lesser than conducting material but higher than semiconductor material are known as insulating material. Insulating, generally the no temperature is passing through effect on the insulating material, but if we are gradually increasing the temperature and suddenly reaches to one very high level or very excessive level, then it convert your insulating material into conducting material, or it may be damage your circuit. Now the last question, that is compare the magnetic circuit and the electric circuit. Generally there are two types of circuit available, electric circuit and the magnetic circuit. The circuit which is easily generating the electric current or electricity is known as electric circuit, and generally the circuit passing the magnetic flux or generating the magnetic flux is known as the magnetic circuit. The first difference is the current is flowing in an electric circuit, the unit for it current is ampere, where in magnetic circuit the flux is generated, where unit for flux is Weber. In electric circuit the EMF is required for flowing the current, whereas magnetomotive force mmf is required for generating the magnetic circuit. EMF is known as a electromotive force. The resistance, the next is the resistance is the property to oppose the current in electrical circuit. So resistance is important parameter in electric circuit, whereas the reluctance, which is equivalence to the resistance in a magnetic circuit, which is the property to oppose the flux. The resistance equation for resistance is delta L by A, whereas R is known as a resistance, where reluctance is denoted as capital S, equals to 1 by mu 0 L by mu 0 into mu R into A. A is a area, mu 0 is a permittivity, free space, mu R is a relative permittivity. Now the next one is a conductance. Conductance is nothing but the 1 by resistance, and permittance is nothing but the 1 by reluctance. The property of opposing the current is known as resistivity. The property of oppose the magnetic flux is known as the reluctivity. The opposite of resistivity is the conductivity. Opposite of reluctivity is the permittivity. The current I equals to EMF by reluctance, and flux phi equals to mmf by reluctance. So this is the difference between the electric circuit and the magnetic circuit. This is also many times asked in our GTU exam. Now just go through some of the important videos for which may be helpful for you to understand the concept of the electrical circuit.
Okay, earlier we had looked at what a half wave rectifier looks like and how it operates. Okay, we realized that a half wave rectifier is basically working during only positive half cycle. Okay, so it was providing me output during only one half of the cycle and the other half is not utilized. Okay, this is something that we do not want. Therefore, its efficiency was very low. We had seen that rectification efficiency for my half wave rectifier was coming out to be around 40.6%, I guess, right? Just around 40-41% efficiency you were getting, and your ripple content in a half wave rectifier was very high. Okay, it was around 121%. Okay, so to overcome these disadvantages of a half wave rectifier, we utilize a full wave rectifier. Okay, so your full wave rectifier basically gives you an output which is something like this. Let's just say this is my full wave rectifier. We are going to look at two configurations of a full wave rectifier. We are going to look at what is a center tapped full wave rectifier and what is a bridge full wave rectifier. But before that, let's just understand what is the output that is given by a full wave rectifier. Okay, so if you have an input AC coming in, let's just suppose that AC looks like this, sinusoidal AC, then what you're going to receive as output is a wave which is going to be like this. Okay, so during positive half cycle you get the same output as input, and during negative half cycle you get your inverted input as output. Okay, so you invert this and you're going to get this. Okay, so your full wave rectifier has an output that basically looks like this. Okay, obviously what I have drawn is a very rough sketch, but you know, this is all these half sine waves are similar. Okay, it is basically your this portion of your input that you're getting as your repeated output. Okay, over here as you can see, your frequency of your output has basically doubled. Okay, this is your frequency or your wavelength over here. Okay, and at the output your wavelength is this much, which is half of this. Okay, so your wavelength is halved and your frequency of your output waveform has doubled as compared to your frequency of your input waveform. Okay, if I have to draw it nicely, then what I can do is something like this. this is my input voltage, okay, and this is my output voltage, okay. So obviously this is repeating and this is repeating as well, okay. This is your V in over here and this is your V out over here. You can define your V out as same as V in between theta ranging from 0 to pi, okay. So between theta ranging from 0 to pi, your V out and V in are same, and between theta ranging from pi to 2 pi, your V out is negative of your V in, okay. So between theta ranging from pi to 2 pi, your V out is minus of V1, okay. So from pi to 2 pi, your V out is minus V in, okay. So in this way you can define your output waveform for a full wave rectifier, okay. Now if I assume my V in to be Vm sin omega t, then I have my equations for my V out, okay. It is equal to Vm sin omega t from 0 to pi and minus Vm sin omega t from pi to 2 pi, okay. Since I have the equations, I can calculate what is RMS and average value for my full wave rectified output, okay.
Thank you.